Welcome to solverfy.
Okay, so we're doing chapter 22, problem 15 here. And it says a long, thin wire, hundreds of meters long, carries a uniform distributed charge of negative 7.2 microcoulombs per meter. So I'm going to call this lambda because it's a linear charge density. And we want to estimate the magnitude and direction of the electric field at points 5 meters perpendicular from the center of the wire. Okay, so the electric field due to a thin wire is given by example 22.6 in the book. You can look that up, and it's E equals 1 over 2 pi epsilon naught times the charge density over the distance away from the wire. So if we want to solve for the magnitude and direction of the field at 5 meters away from the wire, that's just our R equaling 5 meters. So let's go ahead and figure out what the magnitude is, and that's given as 2 times 8.988 times 10 to the 9, and times the linear charge density, which is negative 7.2 microcoulombs per meter, all over 5 meters. And I'm going to write this actually as, instead of microcoulombs per meter, I'm going to do this negative 7.2 times 10 to the negative 6 coulombs per meter. Same thing, just converting to coulombs instead of microcoulombs. So right here, I use 2 times this constant because this is the same as 2k lambda over r. So that's what I did there, just because it's slightly easier. I memorized the k, which is 1 over 4 pi epsilon naught, is usually the quantity easily remembered. So let's plug this in our calculator. We should see immediately that we're going to have a negative left out, so it's going to be a negative charge or a negative electric field. So we'll talk about what that means in a second. If we plug that in, this comes out to being negative 8.6 times 10 to the 4 newtons per coulomb. And now, since it's negative, that means the electric field is pointing towards the wire. And I just realized I copied down the wrong number, so don't take that into account. This is actually negative 2.6 times 10 to the 4 newtons per coulomb. But you probably should have figured that out if you were following along and plugging in your calculator. So we have a negative electric field, so that means it's pointing towards the wire. Awesome. So that was part A. For part B now, we want to use an R equaling 1.5 meters away. So now our equation becomes 2 times 8.988 times 10 to the 9, because that's what k is, times our linear charge density, 7.2 times 10 to the negative 6 coulombs per meter, all over r, which is, oops, not 0, it is all over 1.5 meters. Cool. So now we can plug this in, and we see that E is negative 8.6 times 10 to the 4 newtons per coulomb. So that makes sense. We have a stronger electric field closer to the wire, and it decays as we go farther away, which is what we expect. And since this is negative, it is also, like part A, towards the wire. Awesome. That is it.